Hello students, in this session we'll study few examples from exercise 2.4 of R.R. Goldberg. We'll also take few examples from 2.3, okay, 2.3, 2.4, okay, of R.R. Goldberg. So in that first we'll take example. We have proved result that if Sn converges to L, then mod Sn converges to L. Conversely, if mod Sn converges, then Sn may not be convergent. But if mod Sn is convergent or converges to 0, then we have to show that mod Sn also converges to 0. Okay, so what is our example? Let Sn be sequence, real sequence, such that mod Sn converges to 0. Converges to 0. Then Sn converges to 0. Is the result true? Is the result true? If mod Sn converges to L, converges to L not equal to 0, then Sn converges. So I have to justify it whether it is convergent or not. Okay. Now since limit of mod Sn is given to be 0, what this implies is, therefore for given epsilon greater than 0, there exists positive integer n naught such that mod of mod Sn minus 0 is less than epsilon for any n greater equal n naught. And therefore mod Sn is less than epsilon for any n greater equal n naught 1. But this is same as mod Sn minus 0 is less than epsilon for any n greater equal n naught. This implies is limit of Sn is also 0. Now second part, if limit of Sn mod Sn is L not equal to 0, then Sn may not be convergent. Sn must not be convergent. May not be convergent. Okay. Result is true if I have mod Sn sequence whose all terms are positive, then mod Sn is same as Sn. There is no change. Okay, and that's why we have to take some positive negative terms. Justification. Minus 1 raised to n is oscillatory sequence such that mod of minus 1 raised to n dot etc. tends to 1 as n tends to infinity. So this is oscillatory sequence, means divergent sequence for which modular sequence is convergent, and therefore this part is false. Next example, prove that root of n plus 1 minus root n converges This sequence is convergent. So here Sn is equal to root of n plus 1 minus root n. By rationalizing it, we will get root of n plus 1 minus root n upon root n plus 1 plus root n into root of n plus 1 plus root n. Taking its multiplication, we will get n plus 1 minus n upon root of n plus 1 plus root n. Right? This get cancelled. So this is just 1 upon root of n plus 1 plus root n. Now mod of Sn minus 0 is equal to 1 upon root of n plus 1 plus root n minus 0, which is equal to 1 upon root n plus 1 plus root n. This less equal to 1 upon root n, less equal to 1 upon root n naught for any n greater equal to n naught. Now 1 upon root n naught is less than epsilon. For given epsilon greater than 0, for given epsilon greater than 0, 1 upon root n naught is less than epsilon if only n naught is greater than 1 upon epsilon square. So from 1 and 2, for given epsilon greater than 0, there exists positive integer n naught greater than 1 upon epsilon square such that mod of Sn minus 0 is less than epsilon for any n greater equal n naught. And therefore, Sn is equal to this sequence root of n plus 1 minus root n converges to 0. This sequence converges to 0. Next example, true or false. If sequence of positive number is not bounded, then it diverges to infinity. If Sn is unbounded sequence of positive numbers, then Sn diverges to infinity. So this is false statement. Example, if I take say 1 2 1 3 1 4 and so on, is unbounded sequence of positive number, is unbounded sequence of oscillatory sequence of positive number. As n tending to infinity, you are getting 1. You are getting 1. Means for given m greater than 0, you cannot find n naught such that Sn is greater than m for all n greater equal to n naught. It is impossible because you are getting 1. If I choose m is greater than 1. So that's why our statement is false. Next one, give example of unbounded sequence for which limit of Sn upon n is 0. Example of unbounded sequence for which unbounded sequence Sn such that limit n tends to infinity of Sn upon n is 0. So take Sn is equal to root n. Then Sn is not bounded. Sn is unbounded sequence such that limit Sn upon n is equal to limit 1 upon root n, and it is 0. It is 0. But if you take two sequences Sn and Tn, next example, let Sn and Tn be two real sequences. Sn and Tn are two sequences such that Sn is bounded sequence and limit n tends to infinity of Tn is 0. Then show that, or then prove that limit of Sn Tn is 0. Is 0. So if one sequence converges to 0, other is bounded, then result is true. Okay. So for this, mod of Sn Tn minus 0 is equal to mod Sn into mod Tn for all n. Okay. Now Sn is bounded sequence implies there exists m greater than 0 such that mod of Sn is less equal m for all n. From 1 and 2, mod of Sn Tn minus 0 is less than m times mod Tn for all n greater or equal m naught, or we'll take say for all n, no problem. This is 2 now. Now since Tn converges to 0, since limit of Tn is 0, therefore for given epsilon greater than 0, there exists positive integer n naught such that mod of Tn minus 0 is less than epsilon upon mod m, or if you want to take to m for any n greater or equal m naught. From 2 and 3, okay, this is equivalent to actually mod Sn into mod of Tn minus 0. Right? We are getting this. Right? So from 2, 3, what will get? Mod of Sn Tn minus 0 is less equal m times mod Tn minus 0 is less than m into epsilon by m for any n greater or equal m naught. This implies limit of Sn Tn must be 0. So here if I take one sequence which is bounded and other sequence which converges to 0, then the result is true. But if Sn is bounded and Tn is only convergent, then whether Sn Tn is convergent, that is the question. Note, if Sn is bounded and Tn is convergent, then Sn may not be convergent, may divergent. Justification. If I take again, one sequence is convergent and one is bounded. So Sn is equal to minus 1 raised to n for every n, and Tn is equal to 1 for all n. Then mod Sn is equal to 1 for all n implies Sn is bounded, and limit Tn is equal to 1 implies Tn is convergent. Now Sn which is just minus 1 raised to n, is divergent, is oscillatory sequence. That is divergent sequence. In divergent sequences, we have studied three types: sequence diverging to plus infinity, diverging to minus infinity, and oscillatory. Okay, so with this discussion, today we'll stop our session here. Thanks. Bye bye.